Okay, second example, in a constant pressure process, gaseous n-decane. Please understand that we have normally n-decane will be in liquid state at atmospheric conditions, but if you try to pre-vaporize it by heating it or anything, so you get gaseous n-decane that is fed to the combustion chamber. So this gaseous n-decane and air both at 298 Kelvin they react to form dry products. The composition is given here: 83.61% N2, 4.91% of O2, 10.56% of CO2 and 0.92% of CO. Is a dry combustion. H2O is not there because it is removed after condensing. So dry products. This means that in the reaction you should include H2O. Okay. Now you have to find the heat of combustion, given that the products leave the combustion chamber at 500 Kelvin. So it is not a standard heat of combustion here. Standard heat of combustion means you have to cool the product to 298. Here, since the product is not cooled to that level, it is leaving at 500. You have to calculate the enthalpy of product mixture, taking into the absolute enthalpy of each product to be at 500 Kelvin. Okay. So as we know that when you have dry products composition known, then if we sum up, it will be 100 kilomoles. So to produce 100 kilomoles of dry products, let us assume that x kilomole of n-decane reacts with the air. Okay. So the reaction is given as x times C10H22 plus A times O2 plus 3.76 N2, giving, we do not know the number of moles of H2O now. So that plus all other things as measured by the volumetric analysis, you can write. So 10.56 kilomoles. So 10.56% converts into kilomoles of CO2, 0.92 kilomoles of CO, then 83.61 kilomoles of N2 and 4.91 kilomoles of O2. Now same procedure, use the atom balances to solve the unknowns A, X and B. Okay. Now equation should be written in 1 kilomole basis. If that is the customary thing we do, we do not write the fuel as x kilomoles, we write it as 1 kilomole. So divide throughout by x, you get the equation written in terms of 1 kilomole of decane. So you can see that the products now has this 4.277 O2 and 11 H2O and etc. So this is the thing. Now delta SC, you have to calculate. Initially the reactants are 298 Kelvin. So HR should be calculated at 298 Kelvin. Left us to use only the enthalpy formation of this C10H22. O2 and N2 are 0. Enthalpy formation of O2 and N2 are 0. Similarly, if you take HP, it should be calculated at 500 Kelvin. That means that all the species will now participate in the enthalpies, because even though enthalpy formation of N2 and O2 are 0, sensible enthalpy of O2 and N2 will contribute to the HP value. So let us see how to do that. So now from tables, Stephen Turn's tables or any other NIST website, you can take the HF, heat of formation of decane, is this. So gaseous decane, you have to again choose the enthalpy formation for liquid or gaseous based upon what is the problem you are solving. In this case, we have clearly given that we are dealing with gaseous decane. So you have to take this enthalpy formation. Okay, this is the standard enthalpy formation of I will say gaseous n-decane, correct. So that is taken from the tables. So Stephen Terms gives this value for the gaseous thing. Okay, now that should be substituted for HR. That's it. Now HR is known. HP at 500 Kelvin will be number of moles of H2O is 11 times the molar enthalpy of H2O plus this number of moles of CO2 times HCO2. Similarly, you write for other species. Now using tables, what is this? H2O will be nothing but HF H2O plus delta H H2O at a given temperature, say 500 Kelvin. Okay. So now that is what I am writing here. So for example, H2O enthalpy formation is minus 241,845 and the sensible enthalpy which I have given here 6947, that is the sensible enthalpy of H2O. Similarly, for CO2, enthalpy of formation is minus 393,546 and the sensible enthalpy taken from the tables at 500 Kelvin, corresponding to 500 Kelvin, is 8301. Similarly, you can write for CO, enthalpy formation is minus 110541 and the sensible enthalpy is 5943. But if you see for say nitrogen, 72.83 kilomoles of nitrogen, enthalpy formation is 0, but it has a sensible enthalpy as 500 Kelvin as 5920. Similarly, for oxygen, the sensible enthalpy as 500 Kelvin is 6097. So when you add up this, you get the enthalpy of products. Okay, that then you HR minus HP will give you the delta Hc per kilomole of fuel, or dividing by the molecular weight of the fuel, you will get per kg of fuel. Delta H value is 38,686.61 kilojoule per kilogram of fuel. Okay. So this is the way you do the heat calculation for a mixture. Now this worked example we saw how to calculate the stoichiometric proportions etc. in the previous tutorial, but here we are trying to find the for the same fuel mixture here, we are trying to find the standard heat of combustion when the fuel mixture is burnt in stoichiometric air. Okay. So standard heat of combustion is nothing but when the reactants are at 298, whatever be the mixture, and the products are got and the products are cooled to 298. But here we are trying to do it for stoichiometric combustion. So the only sufficient amount of air is added, but the assumption made is the CO2 remains CO2, no dissociation. Similarly, H2O don't dissociate. Okay. Now the equation, this is a fuel mixture plus oxygen. We can write by balances. So we can just write the equation and balance this and get all the CO2. Please understand that here the CO2 formed plus CO2 already present in the reactant should be added. So we have already seen the example how to get this in the previous tutorial, worked examples previously done for the stoichiometry. So now this is the equation you get. Now find the HR. HR here, please understand that all the HF, it is if you want standard heat of combustion, that means HR should be calculated at so this is evaluated 298 Kelvin. Okay, now that means HFs are involved here. So CO as a HF, so 0.1 times HF of CO plus 0.35 times HF of CH4. H2 I am not including here because H2 delta H, the HF is 0 for H2. Okay. So you can see hydrogen, oxygen, nitrogen are not involved in this because they are basic elements and the heat of formation is 0. So that you should discard. So 0.35 times HF of CH4 plus 0.04 times HF of C2H2 plus 0.02 times HF of CO2 in the fuel. That whatever is in the fuel, that will be the reactant enthalpy HR. Okay. Basic elements are discarded here. Similarly, if you take products, okay, now I am substituting the values. So 0.1 times HFCO is minus 110541, HF of CH4 is minus 74831 and HF of C2H2 is 226748. So again you can get it from the tables and substitute it. Similarly, you have already seen that for carbon dioxide is minus 393546. So once you get this, then you can get the HF value. Now HP value, you have to take this mixture 1.19 times water vapor, 0.55 times carbon dioxide and 4.062 times nitrogen. But anyway, N2 will not appear here because it is a basic element and 298 heat of formation is 0. So 1.19 into HF of H2O plus 0.5 into HF of CO2, that will be this. When substitute this, then you find HF delta Hc by subtracting HP to HR, HR minus HP, that will be this. Okay. So for the fuel you have to calculate this, but if you see that if the reactant or product or at different temperatures, okay, when they enter and exit, then you have to add the appropriate sensibility enthalpies. Okay, the next problem, a liquid alkane CN alkane is CnH2n plus 2. So that is burned. We don't know what is that. Okay, it burned with dry air, and the product composition measured on dry mole basis are 9.6% CO2, 7.3% O2, and 83.1% N2. Okay, that is the thing, product composition dry basis. So H2O we have determined. So what is the standard heat of reaction per kg of fuel and also per kg of oxygen? So we can write the delta HR or delta HC in both per kilomole or per kilogram of fuel, or per kilomole of oxygen, or per kilogram of this, even per kilogram of product. So whatever way you want, you can write that. Okay. Also find the higher heating value. Okay. We have defined higher heating value when in the products. Water vapor is in liquid state, then we get a higher heating value. So how to do that, we will see. Okay. Now you have to importantly understand that this is a liquid fuel. So appropriate value of heat of formation should be used, enthalpy of formation. That is the only thing you should understand. Similarly, when I talk about higher heating value, I should use the enthalpy of water vapor, formation of water vapor in the products as that of the liquids. Okay. Now again, when the dry composition is given, when they sum up to 100 here like this, excluding H2O, now we will assume that a kilomole of fuel burns to produce this 100 kilomole of dry products. So A times Cn H2n plus 2 plus B times O2 plus 3.76 N2 giving 9.6 times CO2, C times H2O, 7.3 times O2 and 83.1 times N2. Now by N balance you get B, O balance you get C, and C balance and H balance will give the values of this AN and A2n plus 2. Now from this you can solve for N, and N comes out to be 12. One more thing is, if you want to do these calculations, you should have enough number of digits after the decimal point. If you don't do that, you will not get 12. If you have enough number of decimal points, then only, see, because very low values are involved, so enough number of decimal points you have to use after the in digits you have to use after the decimal points in order to get a number like this. Okay. So now the fuel is nothing but n-decane, and the value of A is 0.8. Okay. So 0.8 mole kilomoles you burn, you get this product combustion. But anyway, you can divide it and make it 1 kilomole of fuel. But the important thing is, by the dry basis analysis, since you know the C and H ratio here, we have got the fuel itself as n-decane, and that we can refer the tables and get the values, but it should be liquid. Okay. So dividing by 0.8 throughout, you get the equation per kilomole of fuel. So C12H26 plus 27.625 O2 plus 3.76 N2 giving 12 CO2, 13 H2O, 9.125 O2 plus 103.8 N2. So it's excess air. So that comes out of the comes out in the product also. So fuel is in liquid state. What you get as enthalpy formation in the Terns book, tables in the Terns book, is the gaseous enthalpy formation. So that is, you get this value, and the Terns book also lists the HFG value, the latent heat of vaporization. This is latent heat. Okay. So now this values, these both values are available, but please understand that this is given, this enthalpy formation is given in kilojoule per kilomole, but HFG is given in kilojoule per kg. So I multiply by molecular weight. This is the HFG value. I multiply molecular weight to get the value in kilojoule per kilomole. Then I have calculate the value of the this. This is the HR value I get. Okay. HP value is the heat of formation of CO2, enthalpy formation of H2O, multiplied by corresponding number of moles, and you get this value, kilojoule per kilomole of fuel. Okay. Please understand here, this delta HR we seek, though HP minus HR we put, so it is negative. Okay. delta Hc will be positive. Okay. So, when you say calorific value, I have to use delta Hc value. Now, delta Hr here per kg of fuel is just dividing by this molecular weight of this, again is given in the tables. You can use this, some slightly accurate value, use this and divide this by 170.37 to get delta Hr as minus 44,211 for per kg of decane. Okay, now per kg of oxygen we want. So, delta Hr per kg of oxygen, okay, is determined by dividing delta Hr per kg of fuel by the mass of oxygen used for 1 kg of fuel. So, find the oxygen to fuel ratio. Okay. So, 27.625 kilomoles of oxygen is used, that multiplied by the molecular weight of oxygen divided by the molecular weight of fuel, that will be the kg of oxygen used per kg of fuel. So, now that if you divide the delta Hr per kg of fuel divided by that, what you get here? You get the delta Hr value per kg of oxygen burnt. Okay. So, now what is higher calorific value? So, what we have got here is for kg of fuel what you get, okay, delta Hc will be equal to minus delta Hr. So, per kg of fuel is positive now, delta Hr was negative, so negative of the negative will be positive here. So, this is the lower heating value. Why it is lower heating value? Because we the product water vapor in the product here this water vapor in the product 13 times this value is Hf of H2O vapor. So, we have used that. Okay. So, we have assumed when you calculate Hp that the heat of formation of H2O is in vapor state. So, you get lower heating value. For getting the higher heating value, you have to consider all the water in the liquid state. That means for 1 kg fuel 13 into 18 by divided by 170, 1.3737 kilogram of water is produced. So, latent of water is given in per kilomole 44,010. So, per kg it is 44,010 divided by 18 kilojoules per kg. So, that you should add to the lower heating value. So, higher heating value is nothing but lower heating value plus HFG. So, you do this. Now, for 1 kilogram of fuel you get 44,010 divided by 18 kilojoules per kilogram, but you are producing 1.3737 kilograms of water. So, 1.3737 kilograms of water produced into its latent heat in kilojoule per kilogram, that will be added to the lower heating calorific value to get the higher calorific value or higher heating value. Okay. So, this is the way you solve this. So, liquid. So, as I told you, the liquid fuel we have to properly choose the enthalpy of formation for the liquid fuel. Gaseous fuel enthalpy formation is given. So, you have to appropriately use the latent vaporization to get this. So, I have to subtract here. Here it is actually vapor. I am subtracting that to get the liquid, because I want liquid. See, the reactant condition here is liquid alkane. So, what I get from the tables here, this is actually HF fuel which is in gaseous state. So, that minus this is HFG of fuel. When I subtract the HF of fuel which is in vapor state minus the subtract the HFG of fuel to this, then you get this is the HF of the fuel in liquid state. That is what the initial condition is, liquid alkane. So, I subtract this. Okay. Now, when I do the higher heating value calculation, you see that the LHV is added with the HFG of H2O which is produced. So, what is the mass of water will produce, that into HFG, that energy has to be added to this. So, that is what we are getting. Okay. So, this illustrates you have to be careful when choosing the enthalpy formation when by seeing the state of the fuel in the fuel stream and the H2O in the product stream. Okay. Now, worked example 5. A rigid vessel initially contains 2 kilomole of carbon and 2 kilomole of oxygen at 25 degrees and 200 kilopascals. combustion occurs, it is a rigid vessel. So, vessel will not have any volume change. So, combustion occurs at a constant volume, and resulting products consist of 1 kilomole of carbon dioxide, 1 kilomole of carbon monoxide and excess oxygen, and the products are at temperature of 1000. What is the heat transfer to the surroundings? Please understand that this same problem we have done already in the stoichiometry. Now, we are trying to calculate the heat transfer. Okay. The product contains CO2, CO and O2. So, 1 mole and 2.5 moles. But if you take reactants, carbon is in graphite state, that is solid state, and oxygen is in gas state. So, that you have to remember, we have already seen that. So, the state 1 is the reactant state and the state 2 is the product state. So, when I apply the first law to the constant volume process, the heat interaction Q1 to 2 will be equal to the change in internal energy, final internal energy U2 minus initial internal energy U1, that is the product internal energy minus reactant internal energy. The work interaction is 0. So, now as we saw earlier, we have to use the definition of enthalpy and evaluate internal energy in terms of enthalpy. So, U2 is nothing but H2 minus P2V. So, that is written as H2 minus N2 RuT2. Okay. So, number of moles of the product, you know, N2 is number of moles of product, T2 is the temperature which is given as 1000 Kelvin. So, H2 you have to evaluate. H2 is nothing but for this mixture you have to calculate the H2 at 10,000 Kelvin. So, 1 mole of CO2, so HCO2 of 1000, HCO of 1000 and 0.5 H2 of 1000 minus N RuT2, that is N is 2.5, 1 kilomole of CO2, 1 kilomole of CO and 0.5 kilomole of O2. So, 2.5 into Ru is 8.314 in kilojoule per kilomole Kelvin and 1000 Kelvin. So, now at 1000 you see that for CO2 you have enthalpy formation plus the what I put in red is the sensible enthalpy at 1000. Similarly, for CO enthalpy formation sensible enthalpy, for O2 enthalpy formation is 0, sensible enthalpy is added. So, now if you do this, this is the U2. Okay. So, U2 we calculate. Now, U1 is H1 minus P1V equal to H1 minus N1 Ru into T. Now, H1 equal to 0. H1 equal to 0. Please understand why, because C is in solid state, O2 is a basic element, both are basic elements, and the enthalpy formation at 298 is 0, and the reactants are at 298 Kelvin. So, the enthalpy is 0 for the reactants, but U is not 0, U is minus 2 into 8.314 into 298. Please see that N1 here equal to 2, that is 2 kilomoles of O2. The solid will not contribute to the N. So, N1 equal to 2. So, 2 times 8.314 times 298. So, even though the reactants are at 298 Kelvin, enthalpy is 0, but internal energy is not 0. That is having some value here. So, when you do this, Q12 heat interaction will be minus 45334.356 kilojoules, and since it is negative, that means that heat is transferred to the surroundings, and that is this. Okay.